Hi everyone. In today's lesson, we are going to look at leaching, which is also known as solid liquid extraction. The learning outcomes of this lesson would be, in the end, we expect you to be able to distinguish between solid liquid and liquid extraction processes and their applications, and apply the principles of leaching, analyze leaching equipment, as well as calculate material balance and a number of ideal stages for multi-stage leaching. The lesson outcome, we are first going to look at the introduction to solid liquid and liquid extraction processes. Then we are going to look at leaching equilibrium relationship, single stage leaching, multi-stage continuous countercurrent leaching, and also how to calculate material balance and number of ideal stages for multi-stage leaching. Remember, we have spent the previous lesson looking at liquid extraction in detail. We are not going to get into the details of liquid extraction in this lesson. We are just going to touch on it at the beginning. Extraction is a separation process based on difference in solubility. How does this compare with distillation? Remember, distillation is a separation process based on difference in boiling point. Extraction is one of the most useful and widely used separation process techniques in chemical engineering and process operations in general. In particular, we mention metallurgy, where minerals are extracted from the ore. There are two types of extraction. We have solid liquid extraction, which we're going to focus on today, and there's also liquid extraction. In solid liquid extraction, the solute is extracted from the solid using a solvent. And then in liquid extraction, the solute is extracted from the liquid using another liquid which is immiscible in the first liquid. Leaching is a liquid-solid operation where a solid is extracted from a mixture within a solid by contacting it with a liquid solvent. The two phases are in intimate contact, such that the solute can diffuse from the solid into the liquid phase, which causes the components that were originally in the solid to be extracted into the liquid or solvent. A special leaching process where an undesirable component, which is dirt, is removed from the solid, which are clothes, in water, is called washing, which we are all familiar with. Leaching is used to separate the desired solute constituent or remove the undesirable solute component from the solid phase. Leaching is widely used in the biological and food processing industries, such as separation of sugar from sugar beets with hot water, the extraction of oils from peanuts, soybeans, sunflower seeds, cotton seeds, flax seeds, castor beans, and things such as halibut livers. In pharmaceutical industry, many products are obtained by leaching plant roots, leaves, and stems. In the metals processing industry, leaching is used to remove the metals from their ores, which contains many undesirable constituents such as solute salts. Examples are copper salts are leached by dissolving raw copper ores using sulfuric acid or ammonia solutions. Another example is nickel salts are leached using sulfuric acid, ammonia, and oxygen mixtures. In gold extraction, gold is leached using an aqueous sodium cyanide solution. Let us look at the principles of leaching, starting first with definitions and some terminology. The solution phase sometimes is called the overflow or the extract. The solid phase plus its entrained or occluded solution is called the underflow or the raffinate. Considering a system with solute in a solid represented as B to be extracted using solvent C, in most application cases, the concentration of the solute A in the solvent and overflow or extra stream is denoted by X, while that of solute in the solution in the solid or slurry and underflow streams is denoted by Y, as indicated in the figure here below. As you can see, the feed slurry, which is the solid, indicates the concentration of the solute in SY, and then the solids are denoted by B. The liquid or solution in this slurry or solid is denoted by L. Also in the underflow, the same notation is carried through with the solid phase. In the solvent or overflow phase, which is the solution phase, the solution flow is denoted by V, and the concentration of the solute in the solution is denoted by X. The symbols used in this block flow diagram are further defined below here, where V is the mass of overflow solution, XA is the composition of A in the overflow solution, L is the mass of liquid in slurry solution or the solid phase, YA is the composition of A in the slurry solution, B is the mass of dry solid-free solid. This is the mass of solid. N is a ratio, also sometimes referred to as the solid holdup, which is the mass of dry solid-free solid divided by the mass of solution retained in the slurry. In leaching, the solid containing solute is contacted with solvent in order to extract the solute from the solid into the solvent. Upon separation of the two phases, the solution phase normally contains no entrained solids. In some special cases of leaching application, in order to perform equilibrium calculations, it is usually assumed that there is sufficient solvent present so that all the solute in the entering solid can be dissolved into the liquid phase. Also, it is assumed that equilibrium is reached when all the solute in the solid is dissolved into the solution. All the solid is completely dissolved in the first stage of the leaching process. The solid is assumed insoluble, and that no adsorption will happen of the solute into the solid, meaning that the solution in the liquid phase leaving a stage has the same concentration of solute as the solution remaining with the solid matrix in the settled slurry leaving the same stage in the underflow. The settled solid leaving a stage always contains some liquid with it. It always entrains a solution with it. For this special case, as the concentration of solute in the overflow stream is equal to that in the liquid solution accompanying the slurry or the underflow, which is the solution that is entrained in the solids. Hence, on an XY plot, the equilibrium line is on a 45-degree line, which means that X is equals to Y. Equilibrium data for leaching is usually presented as data for the underflow or raffinate phase measured as a holdup of solid by the solution. It does sound a little bit counterintuitive because it is actually the solid that is holding up the liquid, but that's how it is. The equilibrium data is usually presented. There are some presentations where you find that they use the inverse of this, and then the notation for that holdup is given as Ki. This holdup is usually given as a function of the concentration of solute in the entrained solution, which basically is the mass of solute divided by the mass of solution. Equilibrium data for leaching is usually plotted as Ni, which is the solid holdup in the slurry phase, versus Yi, which is the concentration of solute in the solution that is entrained in the slurry, as shown in this figure here. This diagram shows typical equilibrium system where solute A is infinitely soluble in solvent C. The upper curve here represents the curve of N versus Y, which is for the liquid composition entrained in the slurry underflow. The bottom line here, which lies along the x-axis and is not clearly visible, is the overflow liquid where there are no solids, represents the plot for N versus X. As you can see, N is on this axis and then N here is 0, since in the overflow there are no solids. The tie lines which connect the concentration between the solution in the overflow stream, Ya, and the concentration entrained in the underflow stream, Xa, that are leaving the same stage of a leaching operation, are vertical in this situation, indicating that the two concentrations are equal. That is, YA is equals to XA. As you can see, YA and XA are plotted in the same cases. For this case, when the data is translated into the XY plot as shown in this figure, the equilibrium line is a 45-degree line, which is the Y is equals to X line, or the X is equals to Y line. In this next figure, we present to you a generic case where YA is not equals to XA as in the previous case. Also here, the upper curve of N versus YA is for the liquid composition entrained in the slurry underflow, and the bottom line N versus XA, which is on top of the x-axis, and you cannot see it because N is equals to 0, which is the solid holdup in the overflow, since there are no solids in the overflow. Represents the plot of N versus XA. Differently from the earlier case, now the tan lines which connect concentration between the solution in the overflow stream, YA, and the concentration of the solution entrained in the underflow stream, XA, that are leaving the same stage are angled and are not vertical, indicating that the two concentrations are not equal. That is, YA is not equals to XA. The vertical lines, what they do is they indicate what the concentration YA is on this line. And then the angled lines give you the concentration XA that is in equilibrium with this YA, which means that a slurry underflow with a solution containing YA will be in equilibrium with an overflow with a solution containing XA solute. For this case, when the data is translated into the XY plot, as shown in this figure here, the equilibrium line is now a curve, which is much similar to the one we are familiar with from binary distillation. This will be the equilibrium curve now, no longer on a 45-degree line. The equilibrium curve now is similar to what we know from our typical McCabe-Thiele diagrams that we use for binary distillation. Let us now look at material balance for a single-stage leaching system that is shown in the diagram here. We can start looking at a number of balances. We will start with the total solution balance, which is now the balance of component A and component C in solution. We will look at the input of that and the output of that. We know that solution or the liquid is contained in all the streams. So when we look at the total solution balance, we will be looking at all the streams. But here in general practice with the leaching process, we will always look at all the streams. If the streams does not contain solids, if we are looking at the solid concentration and the stream does not contain solid, we will just make it 0. We will make it practice in such a way that we are always looking at all the incoming stream and all the outgoing stream. Looking at the total solution balance, we know that the total solution balance will have the solution in the solid feed, which is LO, and then the solution in the fresh solvent in this. These are the incoming streams, which is now, if we are using pure fresh solvent, will just be the fresh solvent. It will only contain component C. Now looking at the outgoing streams, we will have the solution in the underflow, which is the solution in the stream here, which is will be given by L1. And then we will look at the solution in the overflow stream, which will be given by V1. Because now there will be solute here, it will be both component A and component C in the overflow stream. The next step, we will do solute or component A balance. We will also look at all incoming streams and all outgoing streams. We will first look at the solute in the solids feed, which is given by this concentration YO. Then we will look at the solute in the solvent feed, which will be given by X2. If we are using fresh solvent, it will be 0. On the outgoing streams, we will look at the solute in the underflow, which is the solute here. And then also we will look at the solute in the overflow, which is the solute in the stream here given by a concentration X1. The next we'll look at the solid balance, looking at the input and the output. The first step we'll look at the solids or slurry feed, which will be the solids in the slurry feed, which is given by B. And then we will look at the solids in the fresh solvent feed in here, which will be 0 because we know there's no solids in the fresh solvent feed, but there are cases where you may have solids entrained in the solvent. But as we have made an assumption in the earlier slides, we said that there will be no solids entrained in the solution in the overflow. In the outgoing streams, we will look at the solids in the underflow, still given by B. And then we'll look at the solids in the overflow, which ordinarily will be 0 as there are no solids entrained in the liquid or in the overflow. We will continue still looking at the mass balance. Let us consider a single stage leaching process where V is given in kilogram per hour is the overflow solution with composition XA, which is over here, and with the slurry solution L with composition YA, and the B solids given in flow rate B also in kilogram per hour of dry solids. The mass balance for the system will be solved by the equations we have derived earlier, which are these equations. M is the total flow rate kilogram of the combined streams, which combines A and C. XA and NM are the coordinates for the mixture M on this equilibrium diagram. If you find the coordinates for XA and NM, they will position your point M on the N versus X axis. Using the lever arm rule, we know that L1, M, and V1 lie on a straight line because M separates to form L1 and V1. Using the mixing rule, you know that those 3 points will be connected by a straight line. Similarly, LO, M, and V2, using the mixing rule, we know that they will lie on a straight line. The important part is the composition of L1, which will be here, and the composition of V1, which will be here, will lie on a tie line because those two streams are these streams here, leaving a single stage leaching operation and are in equilibrium. The solution, the overflow solution, and the solution entrained in the solids will have concentrations that can be read from the Y versus the N versus YA and the N versus XA equilibrium lines where they are joined by a tie line. In a situation where the tie lines are angled, it will be something like this, and then you will read your YA here, and then you will get your XA will be here. One important point to note that is If LO entering the system is fresh solid feed with no solvent C present in it, which means that there is no liquid, LO is 0. The position or the coordinates of LO, it will be positioned above N versus YA line. It will not be in the equilibrium line because there will be no solvent in that line. It does not necessarily mean that, sorry, it does not necessarily mean that LO is, my apologies, it does not necessarily mean that LO is 0 because there's still the solute, and remember LO is calculated by the sum of the solute and the solvent. So if the solvent is not present in the solid feed, there's still solute which contributes to LO. What this essentially means that now LO will not be on the N versus Y plot because now there's no solution to talk about. You only have the solute. So the point LO will now be positioned above the N versus Y line. It will not be on the NY versus, it will not be on the N versus YA line, because you will see when we do an example, it will mean that the YA will be equals to 1, so it will be somewhere along this vertical line. Let us now demonstrate the application of what we have covered so far with the use of an example. Let us consider a single-stage leaching of soybean oil from flake soybeans with hexane. 100 kg of soybean containing 20% weight oil is leached with 100 kg of fresh hexane solvent. The value of N for the slurry underflow is essentially constant at 1.5 kg insoluble solid per kilogram solution retained. We are required to calculate the amounts and composition of the overflow V1 and the underflow L1 leaving the stage. Assume the equilibrium for this system is that of Y equals to XA, meaning that the overflow liquid and the solution entrained in the underflow leaving the same stage will have the same concentration. Let's interpret the given information. We are given the feed slurry of 100 kg containing 20% weight, which is that of solute A. This will be in the stream. So that information gives you information that has to do with B, because we can calculate B, which is the flow of solids. Also, we are told that the solvent entering is 100 kg of pure hexane, meaning that X2 will be 0. It will just be pure hexane. Also that N1, which is has to do with the solids entrainments in the underflow solution, is equals to 1.5. So we know that N1 will be equals to 1.5, and we are told that it remains constant throughout, which means that if we are doing a number of stages, this will continue to be 1.5. You can already start to see that if you look at your equilibrium line, instead of being curved like we have seen in the past, it will just now be flat at 1.5. Let us start by looking at the mass of components in the solid or slurry feed. We know that in the feed we have 20% solute. We can therefore calculate the mass of A in the slurry feed, and then we can calculate the mass of solids B, which will be the remaining, which is 80 kg. And then we know there's no solvent, and then we can calculate the mass of solution, which is LO, in the slurry feed, which is only the solute because now there's no solvent. The next step, we can look at the composition of solute in the solution entrained in solid slurry feed. To calculate that, we need the mass of solute and the mass of solution. We know that solution is comprised by solute and solvent, and in the slurry feed there's only solute and no solvent. then we can calculate YO to be equals to 1. And remember what I had elaborated on in the previous slide, that if there is no solvent in the slurry feed, your YO becomes 1. The holdup of solutes by solution entrained in the solid slurry feed for the feed can be calculated, which we know that it will just be mass of solids divided by mass of solution, and solution is made up by A plus C, and we know that it's only A, there's no C, there's no solvent. If we are to plot this information on a N versus Y plot, the LO coordinates will be YO and NO, which are 1 and 4. 1 being YA and 4 being the N, which is the solid holdup. Next, we need to calculate the mass of components and compositions for the solvent feed stream, which is this stream here. We know that it's fresh solvent, so the mass of solute is 0. The mass of solute is 0. There's no solids in the fresh solvent. The mass of solids B is 0. The mass of solvent is given as 100 kilogram of hexane. And then the mass of solution, which will be the combination of solute plus solvent, knowing that the solute is 0 and the solvent is 100, will become 100 kilogram. The composition of solute in the solvent feed stream can be calculated by dividing the amount of solute in the solvent feed stream by the total solution flow, which will be solute divided by solute plus solvent. And we know that there's no solute in the fresh solvent feed stream, as it's given as pure hexane, so that will be 0. The holdup of solutes by solution entrained or solution in the solvent feed, we know that there are no solids in the solvent feed, so that will be 0. If we are to plot this information on a N versus XY diagram, the coordinates of point LO will be given by YO and NO, which will be 0, 0. As you can imagine on a diagram like this, it will be right here in this vertex. We can use material balance to solve the problem further, where we now can calculate the point M, which is the mixing point, which mixes the incoming stream or splits the outgoing stream. It mixes the feed, and also is the mixture of the overflow and the overflow. As you remember, in liquid-liquid extraction, we have two streams mixing to form M, and then those streams again separating to form the extract and the raffinate. This is sort of like a similar approach. So M will be the combination of LO and V, which is the combination of solutions or liquids that are incoming, or it will be the combination, and it is the combination of the liquids that are leaving, which is that of L1 and V1. So what happens is M gets formed when these two mix, and then these two will separate into and M will separate into these two streams, similar as we indicated as in liquid-liquid extraction. So we can calculate M from the known streams that we know, which is the liquid in the stream and the liquid in the stream. Here it's only solute, here it's only solvent. We can further do component balance of A on M. We know that it gets formed by L and V, which are these two streams. So you can do component balance to calculate XM, where we find XM to be 0.016. Next, we do a solid balance. We know that the solid balance can be calculated just using NO and LO, or N1 and L1, it can only be calculated using these two streams that contain solids. We have all information on the stream because we know LO and we know NO. So we can then calculate, and we also know M, then we can calculate NM, which we get to be 0.0667. We can position point M on the N versus Y X diagram at the XM and NM coordinates, which are 0.167 and 0.667. As we have been pointing throughout the solution that the points LOM, V1, V2, L2 can be plotted on the N versus YX equilibrium diagram using the coordinates that we have been stating. We are going to demonstrate how that can be done, which is the graphical presentation of the solution. We are going to follow these steps step by step, showing you how this is done graphically. Since there is only one equilibrium data point, which has been stated to remain constant, we can plot a horizontal line along the given N value of the slurry underflow, which is N is equals to 1.5. Next, we need to remember that XM for the mixture, X1 for the overflow solution, Y1 for the solution entrained in the underflow are all the same as they lie on the same tie line. We can plot a vertical tie line showing these points from the one that is on N is equals to 1.5, which is Y1, and the one that is on N is equals to 0 along the x-axis, which is X1. And then we can also position XM, which we know is at N is equals to 1.6. Next, we can plot LO, which we know is at the coordinates YO, NO, which are 1 and 4, where N is equals to 4. As you can see, we have stated that if there is no solvent in the incoming slurry feed, the point LO will be above the equilibrium line. And although this is a horizontal equilibrium line, this does show you that how LO will be positioned if there is no solvent in the incoming solid slurry. The next point, we will plot V2, which we know is located at X2 and 2, which are both 0, 0 here in the 0, 0 vertex. Then we will draw a line joining LO, M, and V2, as we know they lie on a mixing line. So where this line intersects the vertical tie line, it will be where the point M is located. As you can see, M is located here. Then next we draw the line L1, M, and V1, which is vertical along the tie line. Remember from step 2 above, L1 coordinates are Y1 and 1, and which are 0.165 and 1.5, and V1 coordinates are X1 and O, X1 and N is equals to 0, which are 0.16 and 0. This completes the graphical representation of the solution as it is. Now, what we can do from here is we can use this graphical representation to solve some of the unknowns using the lever arm rule, or we can proceed with mass balance to solve those unknowns. Now we will complete the solution by calculating the material balance to find the masses of L1 and V1, starting off with the total solution balance, which looks at the solution across the mixing M. We know that L1 plus V1 is equals to M, indicating that the mixture does split into the overflow and the underflow. From that equation, we can find an equation that represents V1 in terms of L1. The next we can do the solid balance, which we will do along the solid flow stream. We know that B can be calculated from the solids hold up multiplied by the solution entrained, and the solids hold up multiplied by the solution entrained in the underflow, which gives you the total solids in the mixture. Solving that equation, we can find L1, which is 53.36 kilogram. Please remember the units. I haven't included the units here, which is a bad thing. Sorry, I cannot write using the mouse. It looks very squiggly and ugly. The final step, now we can calculate V1 from the equation that we had derived earlier, which relates V1 to L1, and we find V1 to be 6.64 kilograms. Remember that this balance could have been also solved using the inverse lever arm rule. As you know that with the inverse lever arm rule, we can look at this line segment here, because our target is to find L1 and V1. Sorry, this is L1 and this is V1. And then we know that the line segment L1 V1, this entire line segment represents the mixture M, and then line segment L1, as I've said, please ignore this, L1 M represents V1. Remember the inverse lever arm rule, you always take the segment and the flow or the mass on the opposite end. With this arrangement, you can solve for V1. Then you can look at the line segment on this side in order to calculate L1. You know that line segment L1 V1 is still equals to M here, and line segment M1 V1, which is this line segment here, from the center, from the mixing point to this, represents L1 here. Then you can find this expression that relates L1 to the line segments and the total mixture M. Then you can use a ruler to measure the line segments and then calculate the quantities of L1 and V1. This concludes this lecture. We will be carrying on in the next lecture, where we'll be looking at multi-stage cross-current leaching operation.